Today we are on our last lesson of the year on linear correlation and regression. So just to get into the spirit of what's going on here, do you believe there's a relationship between the amount of time spent studying for a test and the grade you get on the test? Yes, sometimes, maybe. And this is probably based on your experiences, right? If you studied a lot and you got a good grade, well, maybe you think there's a relationship there. How about the age of a car and its value? When you buy a car, it's worth a certain amount. As soon as you drive it off the lot, is it worth the same amount? No, it's already worth less. And then as it gets older, it's probably less and less. What about if it gets really old? Then it's worth more and more. Okay, so there might be some sort of relationship there. How about the height and weight of people? Yeah, so the taller you are, maybe you think the heavier you are. Okay, there might be some sort of relationship there. How about your income level and how smart you are? Ooh. Sometimes. Now, of course, we like to think of lots of examples. So who was it? Bill Gates. He dropped out of college or something, and now he's very rich. Well, I guess I shouldn't even talk about how smart you are and education level are also two different things, right? You don't have to be smart to get an education. All right, so there might be something there, though. Okay. How about how fast you are and how well you play sports? No relationship. What do you think? Maybe. So faster people aren't going to be better at sports? Yeah, it depends on what sport. Okay, if we're talking about track, what about football? Is being faster a good thing? Does it depend what position you play?
Yeah, position between track speed and...
If you're a lineman, big 300-pound lineman, does it matter if you're fast?
Yes.
It is important, right? So maybe there is some sort of connection, how fast you are and how well you play sports. There might be some things like archery. Okay, you could have a lot of time to string your bow and get it going. But anyway, you guys can kind of think about there is some sort of relationship between these things, and the way we're going to answer these questions is not just with random, oh, I think there's a relationship. We had discussion, and we can try to figure it out. But using math and statistics, we can actually say, hey, is there a relationship between two things? And if so, how strong that relationship is. So correlation is what we're talking about there. Okay, so we're going to talk about relationships in terms of correlation. So you can see the word relation. And the correlation will also give a measurement of how strong the relationship is. Now the second part of today is going to be talking about regression. And what that is, it says, well, if two items are related, can we express this mathematically to where we get an equation that's going to relate the two quantities? And if we can get an equation, then we can make predictions and kind of test to see how the relationship works out. So we're going to talk about today specifically linear correlations. So there's lots of different ones, quadratic, quartic, any equation you can think of can have a type of correlation, but we're going to focus specifically on lines, linear correlation. And so we have something called the linear correlation coefficient, and its symbol or letter is going to be R. So anytime you see R, we're talking about the correlation coefficient. And this is a unitless measure. So in all of our problems when we do R, it has nothing to do with what you're talking about. Okay, so if we're talking about IQ tests, okay, it has nothing to do with the score of the IQ. So R is unitless measure, and it describes the strength of the linear relationship. So very importantly here, if your R value is positive, it means there's a positive correlation. So as one variable increases, the other also increases. So that might be like the height and weight example, right? So as your height increases, your weight also increases. Now if the value of R is negative, then you have a negative relationship. It's still a relationship. And what it means is as one variable increases, the other decreases. Okay? We could think of something like as the speed of your car increases, the miles per gallon of your car decreases. Does that make sense? You guys know this. The faster you drive, the worse gas mileage you get. Okay, so as your speed increases, that's one variable. The miles per gallon, the other variable, decreases. And so that's what a negative relationship is. Now the variable r will always be between 1 and -1. And here's a little illustration here. It's a little bow tie. So here, r equals 0 means no correlation. It means there's no relationship. Okay? R equals -1 is the strongest negative correlation you can have. What that means is pretty much all the data lines up in a straight line, and it would have a negative slope here. And here, a strongest positive correlation would be at r equals 1. And then it can have anything in between. So the closer to 0, the weaker the relationship. The closer to 1 or -1, the stronger the relationship. Okay? So let's just talk about positive, negative, or no correlation. How about the time you hold your breath and the amount of oxygen in your bloodstream? Good. This is a negative correlation. So as the time increases, the amount of oxygen decreases. So that's negative correlation. How about the amount of time you've driven and the number of miles on your odometer? That's positive. As one goes up, the other goes up. How about the number of t-shirts you own and the score of your last test? No correlation. So we'd probably have an R of 0 there. How about the temperature of the day and the number of drowning accidents? We might find a positive correlation there. So as the temperatures increase, more people are getting in the water, so the number of drowning accidents might increase. Okay. Now notice here, correlation doesn't always mean causation. So two items can be related, but one may not cause the other. Okay, like the last one, exactly. So because the temperature goes up, it doesn't cause people to drown. We just might see that there's a relationship there. Now, one thing we're going to be using here is called scatter diagrams. And it's a visual aid used with correlation. And it's basically a plot of points, which is bivariate data. Okay, so bivariate just means there's two variables. So we're going to have an independent variable, and that's going to be x, also on the horizontal axis. And this is generally a quantity that can be controlled or something that comes first. And then the dependent variable, or y, is the other variable. It depends on the first one. So if we were talking about the temperature and the drowning one, so it says generally a quantity that can be controlled is the independent, but which one is independent in that example, the temperature and drowning? Yeah, the temperature would be the independent variable. You can't control it, but it kind of is what comes first. All right, and then the dependent variable is kind of the result, and that's how we're setting that up. Now, the value of r is actually a measure of how far a set of points varies from a straight line. Okay? The greater the spread, the weaker the correlation, the closer the r value is to 0. So we're going to see what we mean by that in our next slide. So this is kind of outlining some of the correlations. You can see here, this one's like a straight line. And so r is going to equal 1 in this case. Notice it doesn't have to do with the slope. This is a pretty small slope. It has to do with how straight the line is. Now this one, this is a pretty strong, you can kind of see it's going, they're all going up, so that's pretty strong. This one here, it's going up, but it's getting a little bit more, cloudy as to what's going on. And then over here, notice we really can't make a straight line anywhere. It's just kind of all over the map. So here, r equals -1. You can see this is like a perfect straight line going down. Again, it has nothing to do with the slope other than the fact that it's going down. That's what makes it negative. And then the same type of thing here. This is pretty well grouped together in a line. We can see the trend is going down. And then here there'd be no correlation. It's kind of all over the place. All right, so you guys kind of understand what that measure of r is and the correlation coefficient. That's what we're going to be finding now in our next examples. So go ahead and turn the page. So we're going to draw a scatter diagram answer what type of correlation it is, and actually find that R value, the coefficient of correlation. All right, so here we have the comparison of time studied for a test and a grade received. So we have 10 students, and we've just labeled them 1 through 10. And we have the time studied in minutes here, and the score received as a percent. So the first thing we want to do is draw a scatter diagram. So what we want to do is figure out what the independent variable is and what the dependent variable is. So the independent variable here is going to be the time studied in minutes. We're going to put that on the x or horizontal axis here. And then the score received is the other variable, and that's dependent. Okay, and we have scores 0 through 100, and so we're just going to start with 0, and we'll go up by tens. Oh, this is time in minutes, huh? Yeah. Oh, the time goes, oh, we're still good, 0 through 100. Okay, and then the scores received, that also looks like 0 through 100, so we'll do the same thing here. On the vertical axis. And now what we want to do is plot each data point. Okay, so for our first student, we have the point 20, 40. So we go over 20 minutes, and then up to a score of 40, and we just plot a point. Okay, you can go ahead and plot these along with me. So here's 80 and 92. Let's see, 52 and 80, 60 and 76, 90 and 89, 50 and 70, 100 and 95, 40 and 45, 40 and 60, and one more, 55 and 64. Okay, so that's how you make a scatter plot of the data. And it gives us a nice visual representation. Just like in the game, you can tell something about the relationship just by looking at the picture. So what type of correlation is shown? And let's use this as our example. Is it the strongest positive? Is it a strong positive? Is it a moderate to weak positive? Or no correlation?
Strong positive.
That looks like a pretty strong positive correlation. Now the next question is related to that. It says, what is the coefficient of correlation? In real person terms, what we're saying is, how strong is the correlation? And we're going to put a number to it. So this is where we're going to break out our calculators. And I'm going to focus on the TI 84, 83. So before we do anything, we have to make sure our calculator is set up to do this. It isn't always automatically set up to do this. Maybe yours is. So this is going to be a one-time setup that we're just going to work through together right now. So what we want to do is hit second catalog. So second catalog is going to be second and then the 0 button. Let me zoom out a little bit. So everybody see the 0 button? We got second catalog. And what this does is it lists every function in your entire calculator. It just puts them in a list alphabetically. And so we can scroll down all the way through, but it's going to take us a while to get to where we want to go. So we want to find diagnostic on. So we can scroll all the way down to the D's, or if you notice the little A right here, that stands for alpha mode, and so we can just jump to the D's by pushing the D, which is x to the negative 1. Okay, and that jumps us down to the D's. Now we have to scroll all the way to diagnostic on. then we're just going to hit enter, and then hit enter again, and it just says done. So now we know our diagnostics are on. Pretty exciting. Now we can go ahead and do this. So what we want to do is enter our statistics into our list. We're going to enter them into list 1 and list 2. And we're going to do stat calc and linreg. So let's take a look again at our data values, and we're going to enter them in. So this is the same way you were putting in your data before. So stat, edit. Let's go ahead and clear L1 if it's not already. So you just hit clear and then enter. Okay. Now we want to put the independent variable in L1. So we want to type in all the time studied. So we got 20, 80, 52, 60, 90, 50, 100, 40, 40, and 55. Okay. And you can see here in list 1 the 10th piece of data is 55. There were 10 students, so we're good to go. Scroll over to L2, and we're going to enter in the scores received. So now we have 40, 92, 80, 76, 89, 70, 95, 45, 60, and 64. And you can see there that they match up with 10 pieces of data. Okay. Now we want to push stat and then calc and scroll down to linreg, AX plus B. So we're doing a linear regression. Now if you put more data in to different lists, you can tell it which lists you want to evaluate as independent and dependent. If you used L1 and L2, then you don't have to type anything else in. And you can just hit enter. And it gives you a formula, y equals AX plus B. It gives you an A, a B, an R squared, and an R. So we're going to eventually use the A and the B as well. So we might as well just write these down. So we'll write this down somewhere.
My calculator has A plus BX.
Okay, if you have A plus BX, that's fine. Just when you write out your equation, it's just going to be switched around.
Okay.
So you probably have A equals 29.53.
A equals?
Mm-hmm.
I have A equals, yeah.
Right. So it's just switched around from what we have. So what we want to record right now is the R. We're going to record it to 3 decimal places. Okay. So we're going to say R equals 0.918. So was our prediction correct? Is this a strong positive? Yeah, that's getting up there pretty close to 1. Okay. Now I want to show you a couple other things your calculator can do. It can also do a scatter plot, just like what we had right here. So we want to go to second stat plot, which is the y equals. So go ahead and hit second stat plot.
Oh gosh, wow.
Okay. And then hit enter on plot 1. And then turn the plot on. Everybody with me? We did this before when we were doing, what did we do with them? Oh, we did this one. Now we want to choose the scatter plot. So that's the very first one. See the type? We'll hit scatter plot. And notice now it's asking us for 2 lists, the X list and the Y list. So it should be L1 and L2. And then for the mark, you can really choose anything. It's just how it's going to appear. I like the plus sign. So that our graph looks good and we see all the data, we're going to go ahead and push zoom and then scroll down to zoom stat. Or you can just press 9, zoom stat, and it's going to zoom in right on our statistics. Okay? So you can kind of compare the scatter plot that we made and the scatter plot the computer makes. Okay? So this would be another way that you could do this. to tell what type of correlation was showing. When we look at this, we agree that this is a pretty strong correlation. But how do we tell if this is high enough to say that there's actually a relationship between the amount of time studied and the grade received on the test? Because 0.918, okay, you tell somebody that, yeah, that seems high up by 1, but how do you know? How do you test to see, is there an actual relationship? So this is what we're going to talk about next, is the level of significance. So go ahead and flip to the front page of your notes again. And so now we're on level of significance. The level of significance tells where the cutoff is between a relationship and those factors attributed to chance. That's what you want to write in there. And we actually are going to deal with two major levels of significance, and we call this alphas. Also sometimes called confidence levels. How confident are we that there's a relationship? So an alpha of 0.05 means there's a 5% chance that when you say two variables are related, they actually aren't. Does that make sense? So we say, yes, there is a relationship here, but there's a 5% chance that we could be wrong, and there's not really a relationship. Okay? So 0.05 goes with 5%. Now an alpha of 0.01, this is much more confident. Now it's a 1% chance that when you say a variable is related, they actually aren't. Okay? So you make the statement, yes, there's a relationship, but there's a 1% chance that we're wrong, and there really isn't a relationship. Okay, we're going to test our two levels. So it says, does a relationship exist at the 0.05 level of significance? What we're going to do to be able to tell this is look over here at the critical values and levels of significance. So we have three columns here. N, this is the number of pieces of data, or the sample size. Okay? So this is your sample size. Okay? Now, under the alpha of 0.05, these are your critical values. And then under 0.01, these are your critical values. So here's how we do this. First, we go ahead and find what n is for our problem. Okay, so how many students were we looking at? 10. Okay. And we're going to test at the alpha of 0.05. So what we need to come up with now is our critical value. And I'm going to abbreviate this CV. So let's look in our chart. N equals 10 at an alpha of 0.05 gives us a critical value of 0.632. Okay. Now, if the absolute value of R is bigger than our critical value, then a relationship exists at that level. And I put absolute value of R because R could be negative, right? So let's compare our two. Is our R value bigger than our critical value?
Yeah.
Yes. So what does this mean? There is a relationship. But there's a 5% chance there isn't. So there is a relationship, but there's a 5% chance there isn't. So let's go ahead and test this now at a 0.01 level of significance. So n is still 10. Our alpha now is 0.01. So do you think our critical value is going to go up or down? It's going to go up. It's going to be harder to get a 0.01 level of significance. So what's our critical value? Good. N equals 10. Alpha is 0.01, so 0.765. Okay. And then we're going to compare, is our R value greater than the critical value? Yes, it is. So what does this mean? There is a relationship. But there's a 1% chance there isn't. All right, next up, we want to determine the line of best fit and add it to the scatter diagram above. So let's talk about what the line of best fit is. Okay, so this is back on the first page there. Right, we're going to talk about the linear regression and the line of best fit. So linear regression is the process of determining the linear relationship between two variables. And hopefully you remember the equation of a line. Y equals mx plus b. Remember that? That's going to relate to that ax plus b that we got in our calculator. Okay, so m is the slope, b is the y-intercept, and then x and y are our two variables. So the line of best fit is the line such that the sum of the vertical distances from the line to the data points is a minimum. And you can kind of see that illustrated right here. So fortunately, the calculator is able to do this, where it can create a line, add up all these distances, and it knows that's the smallest distance away. So to determine the line of best fit, we've already done all the work. Okay. We're just going to do this in our calculators again, just so we can go through it one more time. So you want to hit Stat and Calc. And linreg. Now before you hit enter, I want to show you something special here. What we want to do is be able to take this equation and put it into our calculator automatically, so we don't have to type it in again. So to do that, you're going to go ahead and hit the vars button. Okay, see the vars button? Scroll over to yvars, because we want to put it into a y variable. And then you want to choose function. And then tell which function you want to put the equation into. Okay, let's just choose y1. And so now you can see linreg ax plus b y1. Go ahead and hit enter now. And notice it does exactly what we had before. So let's go ahead and write this down. So the line of best fit is going to be y equals 0.7 x plus b, which is 29.5. All right, so if you want to do this by hand, just graphing an equation. So the y-intercept is 29.5, and you just plot it. And then you just pick any other data value. Let's just pick 100. And we want to plug 100 into our equation. Okay. So if we put 100 in here, we actually end up with 99.5. And so we can graph 99.5 right here. Then all you have to do is draw a line between the two. Okay, and you can see it does a pretty good job of approximating all the data there. When we did the yvars thing, if you push y equals now, it put the equation in here for you. So it already did the ax plus b in there. And so if we go to our zoom 9, the calculator graphs it right there. So it'll give you the scatter plot and it'll give you the graph, the line of best fit.
Cool.
Now, the last couple questions says determine the expected grade for a student who studied for these amounts. So we can use it to predict. And you can do it the same way we did up here where you just plug in 30 into these, but it's even easier if you use your calculator. So go to second table set, which is window. Okay, and then change your independent variable to ask. Okay, we got that?
Yeah.
Now go to second table, which is the graph button. And now you should be able to type in these values. So type in 30, and you get 50.78. So 30 minutes, expect a score of 50. Type in 70, you can expect a score of 79.1. And if you type in 90, you can expect a score of 93.3%. Okay, so that's how you would use the line of best fit or regression line to predict data values.
Okay.
All right,
Got it.
that's it.